Yes, you're ready to go.
Yes, welcome everyone to this session on public key cryptanalysis and authenticated key exchange. So with Fabrice Benhamouda, we will monitor the question and introduce the speakers. So we organize in 10 minutes for each talk, like 5 minutes of presentation, then right after the questions that you can ask on the chat on the lib. And or also in you will see if you can unmute yourself during the Zoom. Then our first speaker today is Julian Nowakowski, and he will present his work on partial key exposure attack on short secret exponent CRT-RSA. Julian, it's to you.
Just 1 second, my laptop is doing something strange, but I guess I have it fixed in like 10 seconds. Okay, now it should be fine. You can still hear me?
Yes, we can.
Okay, great. Yeah, so thanks for the introduction. This is joint work with Alexander May and Santanu Sarkar. Before we talk about short secret exponent CRT-RSA, I would like to have a few words on short secret exponent RSA. For that, let me quickly fix some notation. So as usual, in RSA, we denote the public key by a tuple NE, the private key by a tuple ND. Now the point with short secret exponent RSA is that D is significantly smaller than N. We want to discuss the following simple question. How many bits of D do we have to know to break RSA in polynomial time? The answer is quite nice for RSA. It is the smaller D, the less bits you have to know. And in addition, as long as D is really smaller than N, then you have to know less than 100% of the bits. Let's illustrate this a bit. So on the horizontal axis, we draw how large D is in comparison to N. And on the vertical axis, we draw how large of a fraction of bits of D we have to know to break RSA in polynomial time. And as you may know, there are these famous results by Wiener and Bonnet and Durfee, and they show that if we are actually below this 0.292 bound here, well, then you don't have to know any bits at all. But you can show much more than this, and these are these results here, and they nicely extend this. And what you can see is that if you are slightly above this bound of 0.292, then you have to know a really small fraction of bits to break RSA in polynomial time. And then the larger D gets, the more bits you have to know. But as you can see, as long as D really is smaller than N, then less than 100% of the bits of D are sufficient. Now in our paper, we looked at short secret exponent CRT-RSA. The public key is exactly the same as in RSA, but the private key looks a bit different. Instead of having just one secret exponent D, we now have two secret exponents, dp and dq. And here the thing with short secret exponent is that now dp and dq are significantly smaller than the square root of n. And we basically asked the CRT-RSA counterpart of this question here on the left. We asked, how many bits of dp and dq do we have to know to break CRT-RSA in polynomial time? Yeah. So far, pretty much nothing was known for this question, but what we found is basically the perfect counterpart to this here on the left. We found the smaller dp and dq are, the less bits you have to know, and similarly as on the left, if dp and dq really are smaller than the square root of n, then you also have to know less than 100% of the bits. Let's also visualize this. So now we see on the horizontal axis how large dp and dq are, and again on the vertical axis we see how large of a fraction of bits we have to know to break CRT-RSA in polynomial time. And actually, for quite a long time there weren't even results like the Wiener and Bonnet and Durfee results for RSA. Until then, in 2007, Jochems and May finally could show something, and they showed that if you are below 0.073, then you don't have to know any bits at all. Then for 10 years, this was the only thing that we knew, but quite recently, this has been improved by Takayasu, Liu, and Peng, first in 2017, and then shortly after again in 2019. And now we know that actually if you are below 0.122, then you don't have to know any bits at all. The reason that this took so long is that when compared to the attacks on RSA, these 3 attacks here are much more difficult. They are all based on Coppersmith's method, and especially this TLP19 attack is perhaps in all of the Coppersmith type literature the most difficult paper published so far. And therefore it took quite some years until somebody was able to show anything. And what we did now is we took another look at this TLP19 attack and its proof. And what we could do is we could significantly simplify its proof. Especially, we could give much more intuition on the proof than the original work did. And then this intuition helped us to generalize this proof. And with this generalization, we obtained a partial key exposure attack, and its graph looks like this. Yeah, so what we showed is essentially the counterpart to the results already known for RSA. We now know if we are slightly above this bound, the previously known bound, then we have to know a really small fraction of bits, and then the larger dp and dq get, the more bits we have to know. And as long as we are below the square root of n, we really have to know less than 100% of the bits. Okay, I guess that's already everything I can show you in 5 minutes. Much more details, and details on the intuition for our new proof is given in the full version of this talk, which you can find on YouTube. And yeah, thanks for your attention.
Thank you. Thank you for another talk. Are there any questions? I'm checking the Zulip. Or you can ask in the Zoom directly and unmute yourself. So I have a question, and we're waiting for the other to ask. So in your longer talk in the video, you present this nice geometric way of having a intuition on how to improve the polynomial so that the attack will work. So where does this geometric view come from? Like,
so what I skipped in the longer talk for simplicity, there's actually a whole theory behind this called Newton polytopes. We give a bit more on this in the paper. This was already used in RSA by Blömer in May in the early 2000s. I guess that's Eurocrypt paper. It's called a toolkit for solving polynomial equations. And there already something similar appears.
Thank you. And in the maybe in the experiments, so you have to run lattice reduction to reduce the coefficient of the polynomials and then find roots. And so did you use a particular library to run some experiments?
Yeah, we just used the standard things from Sage. Yeah. Okay. So I guess if you use something more clever, perhaps you could get even better results, and stronger experimental results. Yeah.
Okay, so now we have a question from Jancar. Question for Julian. Do you see any possibilities for improvement of the attack anywhere where future work might lead to something interesting?
Yeah, so far our attack only works for exposed least significant bits, and the attacks on RSA usually also work for exposed most significant bits. And we tried some things to also make our attack work for most significant bits, but all the known techniques for RSA, they seem to not translate to CRT-RSA. So this is perhaps interesting to look at, because I guess you have to find some new techniques to get something for that.
Okay, thank you. Maybe if there are no more questions, we will ask the remaining question at the end of the session. And thank you again very much for your talk. And then our next speaker will be Vladimir Sedlacek, and he will present a work on a formula for disaster, a unified approach to elliptical special point-based attack.
Hello, and thanks for the introduction. So let us imagine you are a developer who wants to implement ECC. You have quite many choices to make. You need to decide which curve model you will use, what type of point representation you will choose. Then you need to pick a formula for adding two elliptic curve points. And finally, you need to decide which scalar multiplication algorithm to use. And in our work, we mostly focused on the formula part. So how does an addition formula look like? It takes as inputs two elliptic curve points, and sequentially it computes the output in the same representation. But you already have quite a few choices with these formulas. Here you can see the explicit formulas database, and in the right column, you can see the number of formulas for every specific setup composed of the modal coordinates and representation. So there are really lots of them, but why does it matter to choose the right formula? The thing is that some formulas have exceptional cases, meaning there exist points that when you add them using the formula will give you the wrong result. And in the past, this has really been quite an issue in several big cryptographic libraries. So one of our goals was to try to classify all possible exceptional cases in the EFD formulas. And we used both an automated fuzzing approach as well as manual analysis to do this. And we really did succeed. We went through all these addition and differential addition formulas in the EFD and classified the exceptions. And we found a new family of exceptional points for one specific formula. You can see the family here. Okay, so what do you do when you have these exceptional points? There is the exceptional procedure attack, or EPA, but I don't have time to tell you more about it here. Instead, let me mention that there are also two other attacks that actually do not use exceptional points: refined power analysis, or RPA, and zero value point, or ZVP. But we noticed that these three attacks have quite a lot in common. So another goal of our work was to unify and generalize these attacks in a common framework. So very briefly, how does that look like? The common goal of the attacks is to recover the secret scalar from some ECC implementation. In each of these cases, you have some side channel that can differ. And the common part is, first you guess some prefix of the secret key. Then you construct a special point based on your guess and the given formula. This is important. You give this special point to the implementation, and you can verify if your guess was correct using a side channel. And you just repeat this all over again until you recover all bits of the private key. So to summarize, our contributions are: we released an open source tool for unrolling formulas, which can help you understand better what's going on. We managed to classify all the addition formulas in the EFD and found new exceptions. We designed a unified framework for the three attacks I mentioned, and we also managed to adapt the ZVP attack against window methods, which is quite new. And we also managed to solve new cases of the underlying hard math problem, but it does not help the attacks that much in general, so the problem still remains open. And that's everything for this short overview. Thank you, and if you are interested, you can find more materials at this link. Thanks.
Thank you very much, and thank you for the long talk in the video too. So my question is that how is it common to find such pair of exceptional points like the one you identify for the formula 2007 add BL? Then you obtain that x1 minus y1 0 and x2 y2 0 are are making a failure in the algorithm. I mean, they are giving a 0 that you can identify. Is it common to find such pair of points on any elliptic curve? And are there many pair of such points on any elliptic curves?
Yeah, so in general, like across all the formulas, it's quite a rare find. Like there are cases where you have to distinguish between adding and doubling, and these are mostly well known. But aside from these, this was basically the only exceptional family we found. So from this point of view, it's quite rare. But if you mean
yes, so my question is more, is it a family of points that work on any elliptic curve? Will this attack work with this formula for any elliptic curve?
Yeah, I think so.
Like,
but,
does it depend on some prime p, or is it not related to particularities of a prime p, for example?
No, it should work on any curve. Like it's not, it should not be really hard to find these points. But what is hard is to find these points if you also have the condition that one of them is a multiple by a specific scalar of the other, which is what you actually need to do when you mount the EPA attack. So yeah, it will not be that hard to find these points, but if you want to leverage that for the EPA attack, then that is much harder. But it does not really depend on the curve.
Thank you. Do we have other questions? No question in the chat so far. Then thank you very much for your talk. We will move to the next speaker, and at the end, if there are more questions, then we will ask them. Thank you. So our next speaker is Simon Merz, and he will present cryptanalysis of an Oblivious PRF from supersingular isogenies.
Thanks a lot, Aurore. This was joint work with my co-authors Andrea Basso, Peter Gutesch, Christophe Petit, and Antonio Sanso. An Oblivious pseudorandom function, or short OPRF, is a two-party protocol to evaluate a keyed pseudorandom function. The setting is that the server holds a key K and the client holds an input M. At the end of the protocol, the client should learn the evaluation of the pseudorandom function at Km, but nothing about the key K. And the server should learn nothing about the input or the evaluation of the client. There's some variation called verifiable OPRF, where a server provides an additional proof to the client that he always uses the same key K for evaluations. And these OPRFs have various applications, such as in password-authenticated key exchanges, private set intersection, or privacy-preserving capture codes. Last year at AsiaCrypt, Bor de Kock and Wu presented two OPRFs based on isogenies. One is based on C-side and the other on SIDH. In our analysis, we focused on the OPRF from SIDH. SIDH is a key exchange between two parties introduced by Yao and DeFeo, and the key idea is that two parties compute isogenies of co-prime degrees, which for the sake of this talk, you can just think of as random looking walks in a large graph. And both parties exchange the endpoints, which is an elliptic curve of their walk, as well as some associated information that allows to shift their private isogeny to this new endpoint. And both parties agree on the same shared curve in the picture EMK in the end. So the idea of Bor de Kock and Wu was to transform this into an OPRF as follows. The input of the client is a torsion point that defines the first isogeny. To hide the curve EM and thus information about the private isogeny of the client blinds this walk with another isogeny walk, sends across the end curve on which the server computes their secret walk, which the client unblinds to receive the curve EMK, which allows them to evaluate the OPRF, which is just like a hash of this curve together with some other information. The P in OPRF stands for pseudorandom, and thus without knowledge of the key K, an attacker should not be able to predict the function or evaluate the OPRF without the server's help, even after multiple queries. So if you have one query, then evaluation by the server to get EM0K, and another query from E0 to EM1 evaluated by the server to EM1K, it should be still hard to compute the curve EM prime K. Boni, Coogan, and Wo based the pseudorandomness of their OPRF on a new so-called auxiliary one more assumption. In our paper, we give two attacks on the one more assumption that also break the pseudorandomness of the OPRF. The idea is to recover the curve EK that's in the bottom left of the diagram, as well as three arrows, like the green arrow here in the bottom, for three linearly independent points. And then basically this allows to evaluate the isogeny via the southwest passage instead of the northeast passage as intended of the commutative diagram. So how do we recover the EK and the path to EMK as a malicious client? Say M is a two torsion point that defines the isogeny walk from E0 to EM. Then taking two power multiples of M as a client allows to evaluate or cut short the isogeny walk from E0 to EM, and it basically gives you the points that lie in between EK and EMK. So essentially, using multiple queries, you can recover the entire isogeny from EK to EMK just stepwise. However, the OPRF could defend against such an attack by requiring a proof that the points of the client's input are of full order. Then this is not possible. However, we also give a sub-exponential attack for this case. The idea is that instead of step-by-step walking backwards the isogeny from EM to E0 in our queries, we carefully craft queries of points of full order to build a binary tree where the leaves are the evaluations of the OPRF queries and EK is at the root of the tree. Using multiple meet in the middle steps, this allows to, again, recover the isogeny from EK to EMK. And there's a trade-off between computational costs and the number of queries to the OPRF we need to execute. The only countermeasure so far seems to be to increase the parameters drastically. And it's maybe an interesting future research topic to find more efficient countermeasures. So let me summarize. Our paper provides two attacks on the one more assumption that lead to attacks on the pseudorandomness of the SIDH-based OPRF. We give a proof of concept implementation of the attack, which was implemented in Sage. And finally, something I didn't get around to in this short talk, but I refer to the longer talk and obviously our paper. We discuss in the paper that the starting curve E0 has to be chosen by a trusted setup, as otherwise the OPRF can be either backdoored by the client or a malicious third party, or at least one of the security proofs by Benhamouda et al. Break if the server chooses the starting curve. Thank you for your attention.
Thank you very much for your talk. Are there any questions? So to start then, how can you apply your attack to a system that uses CSID instead of SIDH?
It doesn't apply. The OPRF looks actually completely different. So it's not just, you don't just change one primitive, like the entire protocol looks differently. So for example, in the original paper, the authors only gave a version of a verifiable OPRF in the SIDH case. And the CSID case required to know the class group structure, if I remember correctly. So depending on current discussions about CSID parameters, this might not be actually that practical to instantiate.
Okay, thank you. Other questions? So there is no question in the chat so far. So then thank you very much for your talk, and we will move to the, no, yes, sorry. So there is a, there is a question from Francisco. Francisco, would you like to unmute yourself, or do I ask your question? Yeah.
I guess I can see the question. So it's whether we can produce an isogeny-based Oblivious PRF. First of all, the C-side version does exist. So I guess that's one isogeny-based Oblivious PRF. But otherwise, it's a very interesting question. I think to build an SIDH version that is different from the Bonnet version. So like you could still obviously just raise parameters, but that will be rather impractical given this attack. But otherwise, I think it's an interesting open problem. I don't have an answer for you. Aurore, I think you're muted.
Yeah, Francisco is muted too. I don't know if he's trying to speak then. Yeah. Okay, then we move to the next talk to be sure we are not being late. Thank you again, and so Fabrice is going to continue.
So hi, so welcome to the second part of the session. So the next talk is about symmetric key exchange with full forward security and robust synchronization. This is a paper by Colin Boyd, Gareth Davis, Bor de Kock, Kai Gellert, Tibor Jager, and Liz Miller-Yord. And Bor is giving the talk.
Yes, thanks a lot. Yes, so so this paper is called Symmetric Key Exchange with Full Forward Security and Robust Synchronization. And as mentioned, this is joint work with Colin Boyd, Gareth Davies, Kai Gellert, Tibor Jager, and so the problem we focus on in this paper is how to do authenticated key exchange for very constrained devices using pre-shared symmetric keys. And then this leads to several challenges, and those are, for instance, related to forward security, synchronization, concurrent correctness, and the like. So the contributions that we have in this paper are 3 very efficient AKE protocols with linear key evolution and 2 AKE protocols with nonlinear key evolution. And then we also provide a framework for protocol analysis, and we formalize in this framework several properties, for instance, synchronization robustness, and several more. So what again are we looking at? So an authenticated key exchange is of course a protocol in which Alice and Bob manage to talk to each other using some shared secret, and then they are also convinced that they're talking to the right person. So Alice knows that they're talking to Bob, and Bob knows they're talking to Alice. And then forward security means that if we have several sessions based on the same shared secret, and there is an attacker Eve who manages to steal this shared secret and who maybe even steals the second key, the second session key, then the attacker will not have access to any session before that. So we know that security is not compromised in the past if it is compromised in the future. Achieving this is something that you would normally do with ephemeral key exchange or ephemeral material or development or something, which we of course cannot do now. So instead we will do a key evolution to obtain forward security. And there is some other work related to this, and you generally have 2 flavors. One of them is time-based evolution, and this is, for instance, formalized by Dusti and Yalili in 2015. And you have triggered evolution, where something happening triggers evolving the key to the next step. And in our case, we will use this, and the trigger will be key derivation. So every time you derive a new session key, we will then evolve the key that we will, the static key material, as it were. There are several challenges with this. One of them, of course, being synchronization. So both parties need to have evolved the shared key the same number of steps so that they actually use the shared key. There is some property called concurrent correctness, which means that parallel sessions where one session has evolved the shared key and the other has not, might mean that the key material is not usable for the second session. Or more than two. So in previous work, there are most notably two materials called two protocols called SAKE and SAKE-AM. Both are from Avoyant et al. In 2020, and they do not obtain these properties that we define in our security model. So what is our security model? It's a framework for analysis of this kind of protocols. It is, of course, inspired slightly on the AKE model from Bellary-Rogoway et al., but that model lacks the notion of concurrent correctness, so correctness in the presence of several parallel sessions, and synchronization, which is an important property for us here. And we also, in our model, then formalize synchronization robustness, which means that if something goes wrong in a session, then you can recover from this and compute keys in future sessions afterwards. Which is something that is important to us if we're, again, working on very constrained devices where you cannot just start from scratch because it, for instance, drain the battery. What is then concurrent correctness? Well, say that Alice initializes two sessions with Bob and Bob replies first to the first session before he arrives, before he receives the message from the second session. Then Bob might have evolved his key material, but Alice cannot actually evolve the response based on this material anymore because she has already evolved her key material to start the second session. So this is a problem that we solve in our work. So we managed to recover from this. And there is the property synchronization robustness, which captures the ability of two parties to succeed in exchanging a session key in the future, no matter what has happened in the past. We also show that if the parties get out of sync, then we can resynchronize. And we can define this in a strong and in a weak way. And we say that strong synchronization robustness will mean that all sessions will always terminate successfully, while weak synchronization robustness will mean that all uninterrupted sessions will always terminate successfully. And we show then in our work that this strong version, so that every single session will always terminate successfully, is impossible to obtain with linearly evolving key material. But we show that if we use puncturable PPRFs, then we can actually obtain this. So we can construct protocols in which we evolve the key in a non-linear way as well. Apart from all this modeling work, the result in our paper is 5 new protocols. And so here we see those 5 compared with the existing work. And so we see that all of our protocols obtain the weak version of synchronization robustness. The ones based on nonlinear evolution also have the strong flavor and also have this concurrent correctness in all cases. All our protocols obtain forward security. And it's also worth noting that all our protocols need fewer messages than the existing work. So we improve the state of the art significantly in that way as well. If you're interested in the protocols or in the actual proofs or many more things, I hope that you will find time to watch the full talk on YouTube or read the e-print version of the paper. And then I am thankful that you listened to my talk, and I am here for questions if you have any.
Thank you, Bo. So does anybody ask questions? Okay, so yeah, I don't see any questions. So I have one question for you. So in the paper, you show that the signal protocol, like the double ratcheting ID protocol, is not sufficient for your purpose. But what I was wondering is whether your IDs or your protocol can be used to improve the signal protocol and get more efficiency using like symmetric primitive instead of asymmetric primitive.
That's an interesting question. So what makes this hard to use for Signal is that you will need pre-shared keys. So to initialize, we need to actually put keys on the devices. And that is very suitable for deployment of, for instance, IoT devices or those kind of things, but it might be more challenging for Signal approach. But it's an interesting thought.
No, I meant after managing, let's say you pre-share the key using Diffie-Hellman, and then after you have this pre-shared key, can you just use your protocol instead of reusing asymmetric?
So so I guess you could, and I guess that what we do is, in a sense, it's not super different from this hash-based ratchet that Signal uses after each new message from one user to another. But of course, what Signal does in every new message from one user to the other user is add new key material through a new Diffie-Hellman public key. And then Signal with this not only has forward security, but also what they call backward security, which is something that I don't think we have, which is this complete recovery if everything is compromised completely. I'm now not 100% sure, but I think that is something that we actually cannot obtain with our protocols, while Signal can, because they sample these new keys in every step. And that is something that we don't have the resources for in this model that we use.
Thank you.
Thanks for the question.
Does anyone else have questions? Okay. Okay, so let's move to the next talk, I guess. So the next talk is entitled Security Analysis of CPace. It's by Michel Abdallah, Bjorn Hasse, and Julia Hesse, and Bjorn is giving the talk.
So do you hear me?
Yes.
Okay. So welcome for the advertising session for where I try to motivate you to have a closer look at the full talk and the full paper. So I'd like to convince you that there might be reasons why our paper may be interesting for you, and not only if you're interested in PEG, but also other reasons. So one option might be that you're looking for a way for making reduction arguments of your simulation-based protocol proof more readable. I found it quite hard to understand UC proofs when reading them. And we found a method for formalizing the cryptographic assumption by executable code, so which makes it more transparent in the simulator which strategy is actually used for carrying out the reduction. Second reason might be that you're working on protocols that need to hash on an elliptic curve. So most commonly, the hashing operation is considered as a random oracle, which directly hashes through the curve group. And we went one step further by deriving the exact requirements that we need to have from primitives such as Alligator2 or SWU in order to make the CPace protocol working securely. And finally, of course, it might happen that you are dealing with an application where you were not able to get rid of the password or a PIN. So an efficient PEG might improve the security of your system. That might be the third reason. So CPace is about password-authenticated key exchange, or establishing a high entropy session key by use of a low entropy password. There are already many PEG protocols in the literature. And the specific thing about CPace is that it was designed, we designed it at the time for an application in a very constrained setting, where we tried everything similar to the paper I just presented beforehand, where the asymmetric crypto is the challenge for the computation complexity and power consumptions, and we tried everything to reduce the power consumption for the PEG protocol. And this generates complexity, of course, for the security analysis, because we have some tweaks which are normally not considered in protocol security analysis. So since 2 years, CPace is recommended by CFRG for use in IETF protocols, and this is also part which triggered the more detailed analysis of our paper. To give you an idea, the target platform that Benoit and me had in mind when designing CPace first was an industrial control sensor in a critical infrastructure setting where we had really tight power budgets because of explosion protected environments, and we had really tight memory budgets, and we tried really everything to squeeze the memory and power consumption requirements to the possible minimum. In order to motivate you that PAKE is interesting for constraint device, here's a slide taken from this year's crypto conference, where an analysis has revealed that the current FIDO2 standard could be significantly improved if one authentication step, where the token is authenticated by a PIN, is replaced by a PAKE protocol. And also there we have the situation that we have constraint devices, and also the interest to have a protocol which is more easily protected against side channels. So the CPace paper is mostly on the topic of a quite tedious security analysis, where we tried to capture the implementation tweaks that we have made to improve efficiency. And in order to obtain this and realize this target, we used a method where we formalized the cryptographic assumptions by executable code. So essentially, if you have an assumption, you can generate an experiment algorithm where the experiment generates a challenge, and you try to and you hand over the challenge to some adversary, and you can represent the assumption by the executable code of this experiment algorithm. And what we did is we embed the assumption code in the main code body of the simulator. So it's not separated step for the simulation and a second step for the reduction argument, but we have the reduction integrated in the simulator code. And this has the advantage that we can reuse the same simulator code body and only replace the assumption code for studying the efficiency-tuned protocol variants. For instance, we replace the code which represents the computational Diffie-Hellman assumption with the code that represents the twist-secure computational Diffie-Hellman assumption when working on twist-secure curves. And as a side effect, we think that the reduction strategy becomes more clearly visible in the executable code, because it's you don't have the reduction argument hidden in the last pages of the text body of an appendix of a proof paper, but you directly see it in the simulator code. And this helped us reducing the effort for considering various implementation tweaks. And we think that having a simulator which has the assumptions integrated might also make simulation-based proofs more accessible to machine-based verification. So our results in a nutshell, our analysis has shown that CPace is a fast and secure PAKE protocol, which enjoys composability under strong adaptive adversary models, and the various tweaks that were inserted for constrained devices don't impair security. Second main result is that we were able to derive the exact property that we need from Alligator 2 or the other maps, and we coined this property probabilistic invertibility. So basically, it's the fact that the map needs to have few pre-images. A point generated by the map needs to have few pre-images, and you need to know how many pre-images you can get in the worst case. And third result is as I mentioned before, we formalized the reduction arguments by embedding assumption libraries in the simulator code. And this technique works whenever assumptions are falsifiable, because if you have a falsifiable assumption, you are able to generate an efficient algorithm for the experiment which verifies the assumption. So we would like to, I hope that I motivated you to have a closer look at the paper and the long talk. we also would appreciate review and feedback regarding the current internet draft. We are planning to make a larger review round end of this year. So any feedback there is welcome. Thank you.
Thank you, Bjorn. And does anyone have any question? Okay, so I have one question. Can you extend your result to the asymmetric case? And in particular, maybe I look too fast, but I had the impression that the CPace could easily be transformed into asymmetric pace because you always start by hashing the password, and so I guess the server could just store the hash server. The hash password.
So in fact, originally CPace was a substep in the when I go back to is a substep in the augmented page protocol that we're actually using in this device here, and the protocol, the augmented variant is called AugPace. We have had a publication on it from TCHES 2018, so in Atlanta. So in fact, the CPace has been designed as a subcomponent for the security analysis of the larger construction. And for this reason, it was also important to have a UC proof for the CPace substep, because we use the fact that we can compose this CPace substep in the larger construction.
Oh, I see. So your result automatically carries to the augmented version.
But it's more complex. But that's the topic of the AugPace paper from TCHES 2 years ago.
Okay, that's any other question? Okay. So let's move to the next talk then. The next talk and final talk of the section is titled Modular Design of Road Symmetric Authenticated Key Exchange Protocols. And it's a paper by Xiao Yuting, Chang Rui, and Ma Rui. And Yuting is giving the talk.
Thank you for introduction. This work is collaborated with Rui Zhang and Hui Ma.
Oh, before you begin, can you just put it in full screen mode or play presentation mode, something like that?
Okay.
We're only seeing a portion. Oh, okay. Perfect. Never mind. Thank you.
Thank you. In the literature, there are many strong security models have been put forward for PKI-based AKEs like CK, CK+, ECK, and their extensions. And to date, these strong models were widely accepted to be incomparable with each other, more or less for this reason. Even many protocols have been proposed, but they were merely analyzed in a single model. Thus, in this field of PKI-based AKEs, we still lack a systematic understanding of the prerequisites for constructing secure AKEs. So our essential goal is to give better systematic understandings of AKEs, more specific in the role symmetric setting, where nobody needs to wait and it only involves 2 messages to establish a session key. These are nice properties for practical use. For this, we first made efforts in understanding the security definitions. Thus, we have a succinct and comprehensible unification of the existing models. We also made efforts in constructing methods to make it in a modular way. Putting this together, we also get some new results. There are several important security notions I should introduce here. The first one is perfect forward security, PFS. It states that the the compromise of the long-term keys of both sides do not affect the secrecy of older session keys. The second is a weak version of PFS. It requires that the adversary should be passive when generating the older session keys. The third is key compromise impersonation, KCI. In this attack, the adversary corrupted some party like PI, then it try authenticate itself as some other party PJ to PI. The last is maximal exposure, max. In this attack, the adversary can get keys on both sides, but at most one on each side. The keys include the long-term keys of a party or the ephemeral keys of a session. The ephemeral key, also known as the randomness. We formulated the existing security models as in these tables by exhaustively classifying key secret leakages. In each case, in each model, they can be classified into a security notion we mentioned before. Thus, to achieve secure AKEs, the most important is to achieve these security goals. We also abstracted the raw symmetric AKEs like this. On each side, its computations can be abstracted as three functions, F, FC, F bar, and FC. They are used to compute or recover three key materials, SI, SJ, SIJ. And finally, it will use a KDF to derive a session key from these key materials. With such abstraction, we can describe the paradigm of raw symmetric keys like this. Our starting point is how to securely implement the function pair F bar. This motivates us to define the function key-wise recoverable function KIF, and from these security goals, we define several two security requirements for KIF. And so we have a KIF at hand. We put it back into our modular construction. Our generic description of raw symmetric keys. Thus, we can get our modular constructions easily. Our main results are listed as in these tables. Use a passively secure key exchange protocol to implement FC, and assuming the underlying KIF meets different properties, we can get different secure protocols in these models. Apart from our modular constructions, we also get some other results. We use our modular constructions to explain some existing protocols, but in the CK, CK+, ECK, and ECK PFS models. Of course, according to our results, the same KIF can be used to achieve security in both the CK+ and the ECK models. The same result also holds for the ECK PFS and the CK+ PFS models. In particular, we also give an extension of our results. In the CK PFS model, we give a new construction. It is inspired by the technique used in BJS 15. Of course, we use our observations of our results, which is the result is more efficient than directly applying a compiler to existing protocol secure in the CK model. This compiler is simply by adding signatures on the messages sent by both sides. These are our main results. I can introduce in the 5 minutes. That's all. Is there any question?
Thank you, Yuting, for your talk. So is there any question? Okay, I guess I have a question for you. Like, did you try to study like model in the UC setting?
UC framework?
Yes.
Oh no, I haven't considered the UC framework.
Okay, so if you have any question to Yuting or any other previous speaker, please send it to the chat or like Zulip. Okay. So I think that concludes our session. So we'd like, sorry, we'd like to thank all the speakers again for their talk. And
thank you for the session.
Thank you, Aurore, for presenting the first part of the session. And I think you can all come back tomorrow. So it's 3 AM for me, so I won't be there, but there is an invited talk by Kazue Sako at 8 AM ETC.
Yes, thank you very much, everyone, for participating, and then see you tomorrow.